Welcome back everyone, this is Dr. Gonstein, and here we are again with an RStudio demo, this time for Lecture 6 on multicollinearity. Let's jump right in. Well, I don't need to install any new packages today. We've installed packages in the previous lectures that we needed. So we skipped that step today, and now we're just going to go straight to importing our data. This time it's going to be the Wages3 dataset. So install the data, or import the data. And then let's just kind of jump right into the content. So first, I just want to show you how to generate goodness of fit. So I kind of bundled that into this lecture. So let me just kind of show you how to do goodness of fit here in R. So I'll just generate model 1. Model 1, I'm just calling it model 1. That's the name I'm giving it. It's going to be wage regressed on education experience in female. So just generate that. So the most commonly used measure of goodness of fit is the R squared. So we have R squared reported here automatically in this with using the summary command. We've got R squared and adjusted R squared. But just to kind of show you how to calculate R squared, just so you have an idea of what it is, I'm going to go ahead and kind of show you how to calculate it. Now, the data output shows you what you need to calculate it just from the output, but here in R, I'm going to calculate it by hand. So I'm going to generate the predicted value. So I've already shown you how to do this in previous lectures, so I'll just run that. Here's the predicted value of model 1. And then I'm going to calculate the sum of squares for the regression, and then the sum of squares for the error, and then the total sum of squares. Oh, sorry. The sum of squares residual, the sum of squares explained. Let's just write that in here, just make sure we get it. Sum of squares residual, as the sum of squares not explained, okay? Sum of squares explained, that is explained by the model. And then the total sum of squares. So when I say sum of squares, basically what I'm saying is that it's measuring the amount of variation. So the total sum of squares, that's basically saying the total amount of variation in the wage variable. So the dependent variable is wage, and I want to measure of the total amount of variation in that wage variable. So that's what I have here. What it is that we take the difference between the wage variable and the average of the wage variable, we square it, and then we add that value up. Okay, so that's the total sum of squares, the total amount of variation in the dependent variable. And we are asking ourselves the question, well, how much of that variation in the dependent variable are we explaining with our model? The way that we ask that is we calculate the total amount of variation that is explained by the model. So we do that sum of squares explained. So sum of squares explained is the y hat, that is the predicted value, minus the average of the wage variable. So they're very comparable here. We're basically looking for the difference between the predicted wage value. So y hat is the predicted wage. Okay. So we're looking at the difference between the predicted wage and the average wage. Okay, we square it and sum it up. That's the sum of squares explained. Okay, and then we're going to divide that by the total amount of variation, so the total sum of squares. Okay. Now we also could look at the amount of variation that is not explained by the model. That's the sum of squares residual. What that is it's the actual wage minus the predicted wage squared and then summed up. So let's just go ahead and calculate these numbers. So this number here, actually, I'll run this. Okay, no, here it is. It's reported over here. So we have here the values under the global environment. So the total amount of variation that is not explained, so the sum of squares residual, that's 4,986. All right, so let's look for the amount of variation explained by the model. So there we go. The sum of squares explained, that's 2,236. And then finally, we have the total sum of squares. You can add that up and see that they do add up. The sum of squares explained plus the sum of squares residual equals the total sum of squares. All right, and then R squared is just the amount of variation that is explained by the model divided by the total amount of variation. And so if I run that, I'll get R squared equals 0.3096. And I compare that, R squared is 0.3096. So there we go. So we've just calculated it by hand, what the regression does automatically. All right, so that's goodness of fit real quick, just looking at R squared. All right, now let's check out multicollinearity. So for multicollinearity, we're going to need this car package. Let's just go ahead and run that library. Just tell R that we need that package. So we know multicollinearity is when there's a close linear relationship between multiple variables. That's similar to saying that there's a high amount of correlation. So sometimes if I think that there might be a relationship between variables, I might check the correlation. Education and experience, they could be correlated. Whether someone is married or has children, the relationship between being married and having children, those might be highly correlated. So let's just go ahead and check those out. In this wages, so I'm using the wages 3 data set here. So let's just check that out. Okay, in this particular data set, there's a very strong negative correlation. So that's basically saying that the more time you spend in school, the less time you spent working. So there's a strong negative correlation. Okay, and then if I do married and children, we find a very strong positive correlation. So in this particular data set, there's a very strong relationship between having children and being married, and there's a very strong negative relationship between the amount of education you have and the number of years of experience that you have. Okay, so this is giving us some warning signs. The warning signs are that we could have some multicollinearity. There could be a multicollinearity problem here. So as we know from the lecture, we saw that the real problem that multicollinearity causes is that it will inflate the standard errors on the variables that have multicollinearity. And what that does is it makes it harder for us to reject the null hypothesis that those coefficients, the coefficients on those variables, are statistically significant. Okay, so that's the main problem that multicollinearity creates, and the reason that it inflates those standard errors, if you remember from the equation for the variance of the coefficient, in the denominator there's this term 1 minus r squared. That 1 minus r squared, that r squared refers to the relationship between the independent variables and the other independent variables. If there's multicollinearity, then that r squared is going to be very high. So then 1 minus r squared, it will be very low. That will inflate the value of the variance. If what I'm saying is confusing, please go back to the lecture. You'll see the equation there. So I just want to show you from that, I just want to run a couple quick regressions. I'm going to regress married on children. And I'm going to show you that the r squared is very high. Okay, the r squared is very high. That's a bad sign. That means, again, there's probably going to be multicollinearity here that will inflate the standard errors. I'll do the same thing for education and experience, and again show, okay, the r squared is very high. That gives us some indication that we might have a problem, with multicollinearity. So, actually, I'll skip a step here. So, now my intuition is built. My intuition says that there might be multicollinearity there. I've done a couple of quick things to check for it. It looks like it probably will be there, but let's go ahead and run the regression to see if we have a problem. So here I have a regression. It has education, experience, married, and children, and let's go ahead and run it. So I've run that regression. What do I have? So I find that education and experience are both statistically significant, but married and children are not. Now, if I didn't have multicollinearity, then I could just say, okay, fine, there's my results. But because I am concerned about multicollinearity, I need to check for it. So let me check for it. I'm going to formally, or it's kind of informally check for it, but this is the standard way of doing so, by pulling up the VIFs, the variance inflation factors on my model. So let's pull up the variance inflation factors. Here they are. The variance inflation factor for each of the coefficients in my model. The standard for this is that if you have a variance inflation factor that is greater than 10, then that is considered multicollinearity. So if we check this out, we can see that all of the variables in our model have a variance inflation factor of greater than 10, so we do have multicollinearity. All right. So, but the next step we need to do, all right, so let me just back up for a second. So step number one is I use my intuition to see if I thought I might have multicollinearity. I check some correlations, I check some regressions. All of the signs point to me having multicollinearity. So then when I run my model of wage on education, experience, married, and children, I then check my variance inflation factor, and I confirm my intuition. So my intuition was that I would have multicollinearity, and my variance inflation factor confirms it. I do. If the variance inflation factor is higher than 10, then I have multicollinearity for that variable. All right. Now the next thing I need to do is I need to look back at my model and I need to ask myself a question. I know that all of these variables have multicollinearity. That means their standard errors are too big, all of them, all four of them. All four of them have multicollinearity, so the standard errors are going to be too big for all four of them. Okay, but I need to ask myself a question. For which ones of these variables is my multicollinearity a problem? So here's a little nuance here. Just because I have multicollinearity doesn't mean I have a problem. The only time that I have a problem is if a variable has multicollinearity and it is statistically insignificant. Okay, now why is that? That's because multicollinearity inflates the value of my standard error, which makes it harder to reject the null hypothesis. That is, it makes it harder to conclude that the variable is statistically significant. Okay, so if a variable has multicollinearity, but it is still statistically significant, then there's no problem. So I have no problem with education and experience. They both have multicollinearity, but I have no problem. That multicollinearity is not creating a problem for those two variables. The problem is in married and children. Both variables are statistically insignificant, but I know that they have multicollinearity. So my problem is that I don't know if they should be significant or not. Maybe they should be significant. Maybe they would be significant if I didn't have multicollinearity. But because of the multicollinearity, the standard errors are too high, and so I fail to reject the null. But only because of the multicollinearity. So basically, I don't know if I can trust the statistical test here. I don't know if I can trust these p-values. I don't know if I can trust them because of the multicollinearity. So I have a problem in the married and the children variables. So I have to try to solve it. I don't have to try to solve it for education and experience. I only have to try to solve it for married and children. How do we solve it? We know from the lecture that one way is just to drop a variable. The problem with dropping a variable, though, is that if you think it matters, if you think it's a relevant and important variable conceptually, then you need to include it. You don't want to create omitted variable bias. Now, listen carefully here. These variables are statistically insignificant, but just because they're statistically insignificant doesn't mean they're irrelevant. They might be insignificant because of multicollinearity. So you can't look at these variables and say, oh, well, I can just drop one because they're not significant. No, you can't. They might be insignificant because of the multicollinearity. So you can't use their insignificance as a justification for excluding them. You have to use your intuition, your knowledge, your understanding of what the true model is. And if you think that one of these variables is not important for determining wages, okay, fine, then you can drop it. But you cannot use the statistical significance as a basis for that decision, because they might be insignificant because of the multicollinearity. So you can't go and try to solve multicollinearity by dropping insignificant variables, because it might be the multicollinearity itself causing them to be insignificant. Okay, so we always have to be wary before we go and drop variables, because we might be creating omitted variable bias. So I'm not going to do that this time. I'm not going to drop a variable here. I'm going to say, well, I think both of them are important, so I'm not going to drop either of them. So instead what I'll do is I'm going to create a variable that captures the information of both married and children. There's different ways to do this, and it's always tricky. It's always careful. You have to think, what would make sense? What would be a conceptually reasonable and interpretable combination of these two variables? I'm going to say, I'm going to create a variable called marchild, and it's going to be a dummy variable. It will equal 1 if they are married and have a child, and 0 otherwise. So I'm going to use this if-else command. We've seen this before, except this time it's going to be if they are married and if they have children. If both of those things are true, then my new variable equal 1. If this condition is not true, that if either of them equals 0, then it'll equal 0. So I'll go ahead and create this new variable, marChild, and then I'm going to take out married and children and replace it with marChild. Go ahead and run this new model, and I'll check the variance inflation factor. Okay, now I still have the multicollinearity for education and experience, but again, that's not a problem. But I no longer have multicollinearity with my new variable, marChild, so now I should be able to trust my hypothesis test. Let's see what I find. marChild, I have a coefficient here, but it's not significant. Okay, so now I can be confident in that hypothesis test because there's no multicollinearity. Okay, there we go. I've solved the multicollinearity problem. That's it for today. I hope you enjoyed the lecture, and I'll see you next time.